Hey guys, this is Mr. LaSure again, coming back with another positive physics solution. This is for free fall complete problem set 2, question number 4. We have a football player who kicks a football vertically upwards, causing the football to reach a maximum height of 48 meters before falling back to the ground. We're tasked with determining all unknowns and answering the following questions. With what speed was the football kicked, and what was the football's total flight time? So we're looking for speed and flight time. You can see the answers are there. I'm going to show you how I arrived at those. First thing we're going to do, as we should with all problems, is set up a little table with our variables. We're probably going to want to know things about the initial velocity, maybe the final velocity, definitely a time interval, delta t, maybe its height, h, and lastly, acceleration, right? Now, looking at this problem, we can clearly see that we have limited information. So you might be struggling in trying to figure out where to begin on this problem. Just like the last problem we worked, and anytime we're dealing with free fall and its uniform acceleration, we can identify that the motion is going to follow the shape of a parabola, right? As its velocity is changing every single second over that time interval. We can see that the parabola, which is drawn for you in the image to the left, is going to be used. So with that said, we know something about a parabola. We know at the highest point of the parabola, right, our velocity, v top, let's call it, is going to be equal to 0 meters per second. And based on our conversations from class, we also know the maximum speed that the football or any object being launched upward will be its initial launch speed and the exact same speed when it's on its way down, even with where it was launched. So we have v max is going to be equal to when our football player kicked it. So let's call it v kick. Right? Just to draw in some accelerations, let's kind of think about what gravity is going to do. Gravity is going to be acting downward, right? So we're going to have an acceleration in the down direction. A is going to be acting down. Our velocity is going to be in the up direction. Maybe pick a different color for that. How about we use like a nice purple? Our velocity, when he kicks it, is going to be in the up direction, so v. And maybe we should set a frame of reference now, right? That's the best thing to do anytime we begin a problem. So because our motion is just up and down, I'm going to draw a straight line to represent my frame of reference. And this is the y-axis, and we're going to call up positive. So with this information, let's kind of plug in some values into our data table. We do know the 48 meters for height, so we can kind of plug that in there. Right? But other than that, we don't have anything. Right? So I guess acceleration, we can say, is going to be 10 meters per second squared. And that's a constant near the surface of Earth. But remember, that number changes depending on where in the universe you are. That acceleration is different on the moon and different on Mars and different on every planet. It's a function of gravity and some other variables we'll learn about later. But given this, we can see that if the ball is moving in the up direction, velocities initially will be positive, and therefore gravity must be acting in the negative direction, down. So we have to remember to use the negative sign in our problem set. So because we don't have information about the total flight here, we need to break this off into just the first section of its flight, from when he kicks it all the way up, right to where it gets to the top here. And if we can analyze the first half of flight, then we can make the assumption that everything on the second half of the flight will be a mirror image of the first part, just opposite in direction, and we'll denote that with the sign convention negative. So let's begin this problem. We'll start with this kinematic equation that says v f squared equals v naught squared plus 2 times height. I chose this equation specifically because it's the only equation we have that does not include a delta t. So no delta t. And if we go and we look at our information, we don't have a delta t. So this is actually the only one that's really going to work for us. We don't need to worry about the exact initial velocity or the exact final velocity, because if we pick certain points on this parabola, we can solve for them. That's really quite something. So let's look at what the final velocity would be. If we're analyzing this image from this point to the top point here, right? Our final velocity will be 0. That's going to be the velocity at the top of the parabola. So let's call it v top is equal to, now that initial velocity, that's the velocity when he kicks it. So we'll call it v kick. And we're going to add to that 2, oops, I've got my A up here, times the acceleration due to gravity, g, times the displacement, which for us is the total h. Now let's check. Do we have all this stuff? Do we have a v top? Well, we know that's going to be 0. Check. Do we have v kick? No. That's what we're actually solving for here, right? We do not have that. We know 2 is a constant. Do we have g? Absolutely. And this time we do have the height. So 3 checks, only 1 x. I can move forward and solve this. So let's go and do that. We'll pick that same color. We'll say v top is going to be 0 squared equals v kick. That's what we're solving for. So v kick squared plus 2 times gravity, which for us is 10 meters per second squared, multiplied by our displacement, which is a positive 48 meters in the up direction. So when we evaluate this, the 0 squared is 0. And we still have the v kick squared plus 2 times the negative 10 is a negative 20 times a 48, positive 48. If you evaluate that out, we have v squared of the kick plus, that turns out to be a negative 960, all right, is equal to 0. Now we need to solve for v kick, so let's move the 960 over. We get 960 equals v squared kick. And we have to get rid of that squared variable, so we take the square root of 960, and we get that the v kick is equal to 31 meters per second, which is how we got this. All right. Awesome. So now with that 31 meters per second, we can actually go and use that to solve for the second part, which is the total flight time. We have an equation that says Vf equals V naught plus AT. And let's see if we can use this. We have a Vf. That's going to be at the top of the parabola. Check. We have the kicking velocity, which is our initial velocity. Check. We know gravity, which is 10 meters per second. Check. And we can solve for time, which is the only variable we don't know. So let's go and do that. Vf is our final velocity, 0, equals our initial kicking velocity we solve for as 31, plus gravity is going to be acting down, so it's negative 10 meters per second squared times t. If you solve this, we see that t is equal to 3.1 seconds. Now that 3.1 seconds only represents the part I drew in brown because we are using that v top as 0. So because a parabola has symmetry, we know that the total flight time, if v top is halfway through it, must be 2 times that calculated time. So the total time, t total, equals 3.1 times 2. And we can see that that total time is 6.2 seconds, which verify is what we got right here. So again, it's an approach we need to take when we have limited information. We need to exploit the properties of a parabola. We need to identify that at the highest point, velocity would be 0. We set that point as either our initial or final velocities, depending on how we're analyzing the problem, and then we use the right kinematic equation to solve for the variables of interest. I hope this was helpful. If you have any questions, please email me.